All right, so for section 3.4, special cases with AC method, we will discover special cases that occur when we're using the AC method for factoring. This is in class. This is when you went around in the stations and you kind of discovered these for yourself. And so our math practice that we used was you made viable arguments and you critiqued the reasoning of others because you were working with the groups and you guys were kind of talking it out and you were sharing your ideas and you were both kind of figuring out what the right method was. And so that's why that was the math practice that was used in class. But we are going to learn about 3 different special cases. We're going to kind of go through that discovery again as we make our notes. So what we're going to do is I'm going to show you some examples, and you can work out the examples as I write them. And then I will tell you what the name of the special case was, the pattern that we should see, and then the rule for it. So these methods, you can use the AC method to get to the answer, but these 3 special cases will give us a good shortcut, so we don't need to do that every time. All right, let's go ahead and start. Our first special case, I'm going to give some examples. So first I have x squared plus 6x plus 9. So if I were to go through this whole AC method, I would make my little t-table here. I need numbers that multiply to 9 and add to 6. Well, 3 times 3 is 9. 3 plus 3 is 6. So this works. So if I were to go through my whole AC method, I would have to do x squared plus 3x plus 3x plus 9. I can factor out an x, so I get x plus 3. And then I can factor out a 3, so I get x plus 3. So this is x plus 3 and x plus 3, which is just x plus 3 quantity squared. Now what I want you to look at is this compared to this. What we're seeing is I can take the square root of that, add that number to itself to get this, and that is the number that I have here. So the square root of 9 is 3. 3 plus 3 is 6, and 3 is my number I have over here. That's going to happen every single time when you have a situation like this. And so the name of this special case is the perfect square trinomial. So this occurs when you have a perfect square for your C, and you have that square root times 2 for your B. So that's what you're going to write. You can pause this, write down that for the pattern. So my rule is, if I have a squared plus 2ac plus c squared, that's going to equal the quantity a plus c squared. If I have a squared minus 2ac plus c squared, that's going to equal the quantity a minus c squared. So this works when you have a perfect square in your C position and when you have a perfect square in your A position. So let's do another example now that we know that. So I'm going to give you another one. I'm going to give you x squared plus 10x plus 25. So what I want you to notice is that 25 is a perfect square. The square root of 25 is 5. Well, 5 plus 5 is 10. So I automatically know that this is x plus 5 quantity squared. Now I could go through my whole AC method, make my little t-chart, figure out that my factors are 5 and 5, write out my polynomial, factor by grouping, but I'm going to end up getting this answer. Let's do one more. What about if I have 9p squared minus 24p plus 16? This one's a little trickier to see, but the first thing that should catch my eye is I have a perfect square in both of these spots. So just real quick, before I go through this whole AC method, I'm going to think to myself, well, the square root of 9 is 3. The square root of 16 is 4. 3 times 4 is 12. And 12 times 2 is 24. And that's the number I need right there. So once again, all I did is I took the square root of my perfect squares and I multiplied those together. And then you just have to multiply that by 2, or you need to add it to itself to see if you get the center number. It works here. So I know that I'm going to have 3p minus 4 quantity squared. The 3 comes from the 9. The 4 comes from the 16. And the minus comes from that negative 24. Once again, if I go through the whole AC method, I'm going to end up getting the same thing as my answer. So this is just a shortcut, so I don't have to go through all of that. All right, I'm going to go on to my next special case. This is on the back of your notes. The example that I'm going to show you is x squared plus 3x plus 2. Now, if I were to go through the whole method, I'm going to make my t-table. My numbers need to multiply to 2 and add to 3. Well, 2 times 1 is 2. 2 plus 1 is 3, so that works. So I'm going to go x squared plus 2x plus 1x plus 2. Factor out an x, so I get x plus 2. And factor out a 1 to get x plus 2. So I get x plus 2 times x plus 1. Now what I want you to notice is the relationship between our factors and my binomials and my factored answer. This special case happens only when a equals 1. So that is the name of this case. A equals 1. When a equals 1, once I get my factors, I can go ahead and put those right here into my binomials. And this is going to work every time. I can put them in for the second number of the binomial every single time. So that's the pattern that we see. Once again, go ahead and pause this video for a moment and get something written there for the pattern. My rule for this states x squared plus bx plus c equals x plus m times x plus n. So real quick before we continue on and finish writing this rule, just notice that this is stating that I have a trinomial where a equals 1, and this is my factored answer. Now the m and the n are my two factors that I get from my t-table. So m times n equals c, and m plus n equals b. So m times n are my factors, they equal c, and m plus n equals b. So let's do a couple more examples now that we kind of know that. Our next example will be y squared plus 9y plus 14. So I'm still going to go to the side and figure out what my factors are. So I need to multiply to 14 and add to 9. If I go through my factors, 1 times 14, that doesn't work. 2 times 7, 2 plus 7 is 9. That works. So instead of going through the whole grouping process, I can skip that because I see that a equals 1. And I can go ahead and know that I have y plus 2, I get the 2 right there, times y plus 7. And the 7 comes from here. And that is my final factored answer. So this is just another little shortcut. I'll give you one more. And go ahead and try this one on your own. So once we get this written down, pause the video and try it out. X squared minus 2x minus 15. So go ahead and pause the video, try this out on your own, and once you think you have it, play the video and double check. Or if you get stuck, then you can play the video and I will talk you through it. So on this problem, once again, I'm making my t-table. I need numbers that multiply to negative 15 and add to negative 2. So if I go through my factors, I have 1 times negative 15. That doesn't work. 2 is not a factor. 3 times negative 5. Well, 2 plus negative 5 is negative 2. Or sorry, 3 times negative 5 is negative 15. 3 plus negative 5 is negative 2. So this works. So now I get to skip through all the grouping, and I can go ahead and write this as x plus 3. The 3 comes from here. And x minus 5. And that 5 comes from the negative 5. And that's my final answer. All right, I have one more special case to go through. So this special case, I'll give you an example again and then we'll talk through it. So my example is t squared minus 49. Now if I were to work through this, because I don't know this shortcut, I need two numbers that multiply to negative 49 but add to 0. So I still have my equation here, but my b term isn't there, which means that my b is just 0. So if I go through my factors of 49, I'm trying to think logically about this, and I think, well, negative 7 times positive 7 is negative 49, and those are opposites, so negative 7 plus 7 is 0. So that works. So I'm going to move this over a little bit. So when I write out my next step, I'm going to put my b term back in there, and I have minus 7t plus 7t minus 49. And now I'm going to go through and factor by grouping, so I can take out a t, so I get t minus 7. I can take out a 7 and I get t minus 7. So I end up with t minus 7 and t plus 7. Now, I'm going to focus on this and this. So notice that I have a perfect square here. and these numbers happen to be the square root of that. And then the subtraction is very important to this also. So the name of this special case is difference of squares. So I have difference of squares. So this occurs whenever I have a perfect square here and a perfect square here, and then I have them subtracted. And so that's my pattern. And I always end up with something like this. And so my rule is whenever I have a squared minus c squared, I end up with a plus c times a minus c. So I'm always going to have the plus and the minus, and I'm going to have the square roots and the square root. So let's do a couple other examples. My next example, I'll do x squared minus 16. And so instead of going through the whole process, I'll notice this right here is a perfect square, and this right here is a perfect square, and I'm subtracting them. So my answer is going to be x minus 4 times x plus 4. Or I could write this x plus 4, x minus 4. It doesn't matter which order. So the square root of x squared is x. The square root of 16 is 4. So that's where those two numbers came from. And then I always have the plus and the minus. Let's do one more. So this time I have 4y squared minus 121. Well, 4y squared is a perfect square, 121 is a perfect square, and I have my subtraction. So when I write this out, I need to think the square root of 4y squared is 2y. The square root of 121 is 11. So I have 2y plus 11 times 2y minus 11, and that is my answer. So these are our 3 special cases, and once again, these are ones that you should study because they're shortcuts, so you don't need to go through the whole AC method every single time. I highly recommend that you take some time, study these, practice them, start noticing the patterns so that you can use these in the future. All right, you're good to move on to your homework. You have one section where you are going to factor them, and then you have another section where you're going to solve them, and you're going to solve them just like we've been solving every other factored problem in this unit.